everybody, my name is Professor Soborno and today we're going to be looking at some more physics. So this is physics number 124. We're getting close to 200. So today we're going to be looking at relativity, time dilation. Now our problem is going to be the lifetime of a muon. The purpose is just getting an example of time dilation in real life. So, what are muons, first of all? They're like little tiny particles that are emitted from the sun. I believe they're forms of radiation. Now, they go very, very fast at speeds that could be comparable to the speed of light. And these, in turn, they have some very short lifetimes. That's 2.2 nanoseconds. For context, that's equal to 2.2 times 10 to the negative 6th power. For even more primitive representation, we can just write it like this: 0.1234522 seconds. Now think about that. That's almost an instant. So yeah, that's a very small amount of time. And that's the lifetime of a muon as perceived from its own perspective. However, what if there's a muon going at, say, going at, say, 60% the speed of light? Obviously, as one said, when it's observing from its own perspective, the muon only has a lifetime of 2.2 nanoseconds. We'll be measuring in nanoseconds for the whole calculation, so I don't have to deal with scientific notation. So, we're going to try to find the time, the lifetime of a muon from the observer, from a reference frame of an observer at rest, watching this absurd scene play out. Now, first of all, 60% C will have to convert to 0.6 C. So now, with that over with, we'll have to look at this. So, this is a common example of time dilation. We have three little things here. We have three variables here. One of them is unknown. And these all look familiar. That's right. They're inserted in the equation of time dilation. Of course, this is how it works. V over C squared, whole squared. We don't need to write the gamma notation here because that's just useless and will take more steps. So, that makes this T mute over the square root of, so we know T mute is going to be 2.2 nanoseconds. Sorry for all the absurd banging. And then we have 1 minus, 0.6 C meters per second over C squared. I don't think we need to put meters per second. So now these cancel out. Sorry for the dropping of that cap. So now, since those cancel out, we get 2.2 nanoseconds over the square root of 1 minus 0.6 whole squared. Please excuse that. So now, 2.2 nanoseconds over the square root of 1 minus 0.6 squared is equal to 0.36, I believe. Now, that's going to be equal to 2.2 nanoseconds over square root of 0.64, which gives us 2.2 nanoseconds over square root of 0.64 is 0.8, I think. now this is a case of basic division. So 2.2, 0.8. Let me do some decimal math. This is going to be 1.6, remainder 0.6, and this is going to go in twice. So that's going to be 2, and then the next number 0.6.8, which is also equal to 3/4. Sorry if I'm writing this in too primitive notation. 3/4 is actually 0.75. So that's what we have over. That's the new lifetime of our little muon over here. That's the dilation of time we have. So let's see the percentage of which its lifetime has changed from an observer's rest perspective. Okay, so new minus old over old plus 100%, I believe. No, this is just okay. So now
times 100.
Oh, times 100. Yeah, that's true. So that's going to be equal to n minus o over o. New is equal to, okay, so our new one is 2.75. Our old one is 2.2. That's just going to give us 0.55. 0.55, our old one was 2.2 times 100 is going to be equal to, okay, to 0.55, 2.2. So that's equal to 1.1 over 4.4 times 100, which is equal to 1/4 at 0.25 times 100, which is equal to 25%. 25%. So that means that this has a multiplier. The muon's lifetime has a multiplier of, oh my god, 125%. So now it's new. This is our new lifetime. So now this doesn't differ too much from the old one, as 0.55 nanoseconds would actually look like this. But still, it's a countable difference. So now, thank you everybody for watching, and bye bye everybody. See you later.
How was the sound?